Welcome to the second part of lecture 3, and this time we are going to talk about class of ill-posed problems. A class of problem is known as ill-posed problems if either of the following features exist. A unique solution does not exist. Unique solution does exist but computationally not feasible. Unique solution does exist but unreliable. Now, the first case when I'm saying that unique solution does not exist, the one example of such problem is when the problem of variable selection in large P small n problem setup. These are considered as ill-posed problems. For the second problem is unique solution exists but computationally not feasible. Second problem is has the second example goes to the second problem, which is problem of variable selection in large P considered as ill-posed problems for model complexity, because if you're using forward stepwise selection or backward stepwise selections, any kind of stepwise selection for very large P will becomes a very cumbersome. You have to fit too many models, and that might be infeasible in terms of implementation. And the third problem is unique solution exists but solutions are unreliable. Problems of multicollinearity is the third kind of problem, ill-posed problem, whether you have a unique solution but it is unreliable. So let us investigate the first problem or first class of ill-posed problem a little bit detail. Unique solution does not exist at all. So say consider the problem of variable selection in large P small n setup. Such problems are very common in medical sciences. For example, in a study of the efficacy of treatment, suppose a study randomly chose to observe 100 patients. It means your sample size is n is 100. Now scientist wants to collect thousands of test results from each patient, from say regular glucose level to genetic marker, all kind of tests they can do from each patient. So it means the number of features, the P is 1000. So in that kind of scenario, of course, you don't have a unique solution. You can have infinitely many solution, but that is not a practical solution. But you don't have a unique solution, so that is a little bit of a challenge. Now, why it is challenge? Because if you don't have a unique solution and you say, oh, I have infinitely many solution in such kind of problem, you have beta equal to 0 is also a possible true solution. It means none of the feature on your study has significant effect on your target variable y. Now suppose your target variable is uh, a particular disease or not, or a particular level of glucose level of a particular patient. Now you have spent thousands of dollars, hundred thousands of dollars, or you have spent crores of rupees to collect these data, and you are saying that the genetic marker which is most likely to have an effect on your target variable has no effect. So that's a problem. I mean, you have all kind of scientific evidence that a particular feature, a set of features, does have an effect, and if you say that, oh, my unique solution does not exist, is not a very reliable answer to the greater scientific community. So it's a mathematical problem. You have to address this mathematical challenge. Let's consider the second class of ill-posed problems. So where unique solution does exist but computationally not feasible. So let's consider the problem of the variable selection in very large P uh, can be considered as a ill-posed problem. Suppose you're working in a credit rating company, okay, where you're working with a huge customer database. The number of customer in your database is more than 100,000, and for each customer you have thousands of features. Now we know for large data set, if you apply stepwise selection algorithm, that it has to fit 1 in plus p into p plus 1 by 2 many models. If p is 1000, then you have to fit 500,000 plus many models to get the best, I mean, get the some reasonable good solution. So it makes several days to complete your job. However, oftentimes in corporate environment, you do not have several days, and upper management wants the result by end of the day. Uh, these are the scenario where theoretically you have a unique solution and a good solution, but computationally not feasible. So this is, we can categorize this kind of problems as a ill-posed problem or second class of ill-posed problem. Third class of ill-posed problems is basically unique solution exists but unreliable, and problem of multicollinearity also considered as a ill-posed problems, and this is a third type of ill-posed problems that we are talking about. Multicollinearity is an interesting problem in a sense you have an unique solution. However, it is not reliable because standard error becomes so large that you cannot do a reliable statistical inference. In a sense, again, the same problem that your multicollinearity becomes so large that you are saying that okay, my the weight of a car is has no effect on the miles per gallon. That means you can have a very high, you're effectively you're saying that okay, you can have a car with a very high load, but your miles per gallon will have, it will not have any effect on miles per gallon. So naturally it doesn't make sense. Engineers will laugh at us if we does this kind of you know silly inference. So multicollinearity is another third kind of problems which can be classified as a ill-posed problems. So the question is how to regularize an ill-posed problem so that we can have a some sensible solution. A Russian mathematician, Andrei Tikhonov, proposed a solution for this kind of problems, called, typically known as Tikhonov regularization or simply regularization. He tries to find a solution for ill-posed problems by imposing certain restrictions or conditions on the solution space. If solution can be obtained, then we can say the process as a regularization of the ill-posed problem. So that is what. Now, how we regularize the ill-posed problem? The idea of Tikhonov regularization is you penalize the objective function. How you penalize? So the class of functions, so this is typically, suppose called, this is your residual sum of square of the function you want to estimate plus a penalty function you add, and you try to optimize that. So, and lambda is the amount which control the penalty. So if you lambda is 0, there is no penalty, then it is simple residual sum of squares. And so if I take f of x equal to x beta, then my residual sum of squares of beta is y minus x beta transpose y minus x beta. Now if I take lambda equal to 0, then this penalty is 0. I'm not imposing any penalty, whereas and then this becomes negligible, this becomes null, and then it is only residual sum of squares, this part, and solution for that will be OLS estimator. But if you put a penalty, then it will some oftentimes it gives you it's regularize the solution, it gives you a solution. And how it works, I will talk about it. Here we have taken a L2 norm or the residual sum of squares as the objective. One can take L2 L1 norm, but we will only focus on L2 norm for our purpose. Now, what penalty to choose? The most popular penalty is typically the L2 norm penalty, which is beta minus beta 0 transpose beta minus beta 0. You typically choose beta 0 equal to 0, then the penalty looks like a beta transpose beta. Now, let us look into the you know the solution or the proposed solution. So in standard ordinary least square method, we only try to minimize this part, residual sum of squares. Now Tikhonov regularization is saying that you minimize this plus a penalty is lambda equal to beta transpose beta. Now, if you solve this, if you minimize this entire thing, then what you get is Ridge solution. The Ridge solutions, we can write it as an argument of the minimization problem of this y minus x beta transpose y minus x beta plus lambda times beta transpose beta. Now, this minimization problem can be equivalently rewrite this, also known as the Ridge problem, as minimize the residual sum of squares y minus x beta transpose y minus x beta. This is the residual sum of squares of errors, RSSE, subject to this minimization. In the ordinary square method, you don't have any restrictions. It is unrestricted minimization. Here you are doing a minimization with a restriction, and the restriction is subject to beta transpose beta is less than equal to t. It's like I'm giving a budget that, and beta has to be constrained within that, and which makes it explicit the size of the constraint on the parameters, and as a result you end up regularize the problem, you get a solution for these problems. Now this lambda and t, one can show that mathematically they are one-to-one function, but we never see any explicit relationship or a known function or known relationship which can explain lambda as a function of t or t as a function of lambda. But from the construction we can say lambda and t has a one-to-one correspondence between them. Turns out that Ridge problem has an analytical solution. This, if you minimize this y minus x beta transpose y minus x beta, this residual sum of squares of error plus this constraint, or the plus this sort of a Lagrange multiplier kind of penalty terms, then the Ridge analytical solution for the beta, the Ridge solution beta, is x transpose x plus lambda I inverse x transpose y, and the I is the p cross p matrix, lambda is the symbol, this parameter, tuning parameter, also known as sometimes tuning parameter. Ridge solution is a special case of Tikhonov solution, we can say that. Now this result into We will move on to another interesting regression called LASSO regression, often known as LASSO is the abbreviation of least absolute shrinkage and selection operator. The lasso is a shrinkage method like reach method with a subtle but very important difference. The difference is in the penalty. If you go and look into the reach solution, it is also minimizing residual sum of squares of errors with the L2 penalty. Here you are also minimizing residual sum of squares of error but with L1 penalty. And this lasso optimization can be equivalently expressed as uh, arg mean of y minus x beta transpose y minus x beta. So you are minimizing residual sum of squares of error subject to sum of mod of beta j less than equal to t. Now, if you basically, I'm giving a budget to total how much this beta j's can be, and if we push this t to very small, small positive value, then what will happen? Many of the beta j's will goes to zero, very close to zero. In that way, some of the beta j will end up at zero beta j's. So that means basically we are going to drop those features variable, the beta the fe, bet, the features for which beta j turns out to be zero in the solution. You can essentially say that these features will have no effect on the target variable and you can drop them from your model. So Lasso does not have a closed form solution like Reach. Computing the Lasso solution is a quadratic programming problem, and efficient algorithms are available for computing the entire path of the solution as you vary the lambda with some same computational cost as the ridge regression. So this is a very good news for us actually. Because of the nature of the constraint, making the t sufficiently small will cause some of the coefficient to be exactly zero for lasso, and that makes lasso to or does a kind of a continuous subset selection, because if a beta j becomes zero, exactly zero, then effectively you are dropping that feature from your uh, regression models. So reach takes care of the multicollinearity kind of issues. The reach regression takes care of the multicollinearity of the kind of issue. In the reach regression, your penalty is not very strong. It is not strong enough to make all the beta j's to force it to goes to zero. So typically in the reach regression, most of the time we find that beta j may go to become smaller, goes to zero, but not necessarily it will be exactly zero. It will be small value, but it will not be zero. But in the lasso regression, it does make the beta j's goes to zero. So this is an interesting feature. So lasso regression does a feature selection. Naturally, it does a feature selection. And here is the interesting thing. In the stepwise selection, if you have p many features, you are fitting 1 plus p into p plus 1 by 2 many models separately, and you are trying to find the best model out of those many models. So if you have about 100 features, you have to fit 5000 plus many models to get the some good models. But in the lasso selection, all you are doing fitting one model using a one constraint optimization, this constraint optimization, and in one shot you are getting the best models. And that is where a real clever trick comes into the picture. So it basically makes the stepwise selection obsolete in terms of feature selection. Why? Because in the stepwise selection, what you are doing is effectively you are fitting thousands of models, and then you are trying to get the one model out of it. But in the lasso regression, what you are doing, you fit one regression model, but you're doing this optimization in a clever way, in a sense the features which does not have effect on y, you make their beta goes to 0. You will force them to your the optimization is con- construction of the optimization is being done in such a way that its beta will force to go to 0. If beta is forced to go to 0, then effectively you are saying that feature does not have any effect, so you drop that features. So if you have say 100 features, out of that 80 of the features, if their beta goes to 0, in one shot you are dropping all the features and you're getting all the important variables in one shot, and you just get the best model. So that is what the idea of lasso regression. It's a huge jump in terms of computational ability to feature selection. Uh, One of the problem with ridge regression and the lasso regression is ridge regression does take care of the multicollinearity issue, but it does not take care of the feature selection. On the lasso regression, on the other hand, does a very good feature selection, but it does not take care of the multicollinearity issue that much. So, uh, Zhao and Hesty in 2005 they developed something called elastic net regression or elastic net penalty. They put the penalty in that way in this structure, and it turns out elastic net does take care of both uh, feature selection as well as the multicollinearity issue. Tikhonov regularization for multicollinearity and the feature selection was developed over almost 3 decades or 4 decades. Though Andrei Tikhonov gave the solution for the system of equations, which does not have a yield solutions, so he was trying to develop a solution for those kind of problems. Reach, Hoerl and Kennard in 1970 developed the ridge regression for to take care of the multicollinearity issue. But at that time, there were in the Soviet bloc and the American bloc were not in communication. They were not aware of uh, the Andrei Tikhonov works. So in the 1970 paper, there is no reference of the Andrei Tikhonov's work. But later in 2000, I think, or in 90s, they wrote another paper, sort of a review on this area. At that time, they did recognize about Tikhonov results from 1943. Lasso regression takes care of the feature selection. It was done by Tipshirani in 1996, and elastic net regression takes care of the both feature selection and the multicollinearity. It was done by Zhao and Hesty in 2006. So, and Tipshirani and Hesty is the person who wrote this Elements of Statistical Learning book, which most of my materials are coming from this book. Now the time has come, we will start doing some hands-on. So please continue watching these videos. In the next part, we will resume the hands-on. Thank you very much.